Okay, good morning, afternoon, or evening, everybody. Welcome to the Moving Code to the Data, Analyzing Sea Level Rise Using Earthdata in the Cloud, Earthdata webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. What I'll do first, I'll begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any questions or you have any issues, what I'd like you to do is enter those into the Q&A panel rather than the chat, and you can find that located on the right side of your screen. Today's webinar is being recorded. The recording will be posted both to the NASA Earthdata website and to our NASA Earthdata YouTube channel within a week of completion. And a bit later on, I will paste those links into the chat for all of you so you can reference them later. Once completed, I will send an email to all registrants with recording links and also a link to the presentation slide deck used in today's webinar. As far as timing is concerned, today's webinar will be 1 hour and 15 minutes long, with 1 hour allocated to the presentation and demonstrations and an additional 15 minutes for the question and answer period. During today's webinar, we will have two speakers. Our first speaker is Ed Armstrong. Ed is the Data Engineering Lead at NASA's Physical Oceanography Distributed Active Archive Center, or PODAC. Our second speaker for this afternoon's event is Jinbo Wong. Jinbo is the Project Scientist for NASA's PODAC. Ed will begin today's webinar, and actually let me move forward here so you can see that. Next slide. Ed will begin today's webinar with an introduction to PODAC, its missions, and also the data. And then from there, he will provide information about global sea level measurement, trends, and data sets. And finally, we'll conduct a demo where he will visualize sea surface height anomaly data using PODAC's State of the Ocean, or SOTO tool. Once finished, we will transition over to our second speaker. Jinbo will take you through a step-by-step tutorial from setting up an AWS account, and he'll show you how to conduct cloud computing using altimetry data for scientific analysis and investigation. Once he is finished with his demonstrations, we will transition to a final optional set of polling questions. And generally, I'll give these questions about 5 minutes or so within the webinar context, but I will leave it open much longer than that for those of you who may wish to answer those questions, and we certainly do appreciate your feedback. From there, we'll move directly to the Q&A session. I would like to say that depending upon the volume of questions we receive, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line, but we do have a hard cutoff of 3:15 p.m. Just a really quick note about the Q&A period. We try to answer all the questions within the time allotted, but if we are not able to address your question during Q&A, our speakers will follow up with you offline. With that, it is my pleasure to introduce today's first speaker, Ed Armstrong. And Ed, at this point, let me stop sharing my screen and toss the presenter role over to you.
Thank you, Jennifer, and welcome everybody.
My
name is Ed Armstrong. Yes, thank you. Let me start sharing my screen. And I'll start the slide presentation now. Welcome everybody, I'm Ed Armstrong, and I'm here with my colleague Jinbo Wong. We both work at the Physical Oceanography DAAC at the NASA Jet Propulsion Laboratory in Pasadena, California. And our talk today is entitled Moving Code to the Data, Analyzing Sea Level Rise Using Earth Data in the Cloud. And so as we're moving in this exciting era of cloud computing, and as NASA moves more of its data into cloud, really this presentation we hope will give you a practical introduction into just the entire workflow, beginning with establishing an AWS account, and then working with some of the products that I described and actually generating, running some scientific code and generating a climate signal. So that's what we hope to get out at the end of the day. And I'm gonna turn my camera off now just to save a little bit of bandwidth. I just wanted to say hello to everybody. So just to reprise a little bit about what this webinar will cover, I'll give a brief introduction to PODAC and its missions, and then I'll note the previous Earthdata webinar on cloud data, on PODAC cloud data and the technologies. It's kind of give a background to the community. And then move on to introduce global sea level measurements and their trends on the data sets that are used to observe that, and then show some of these features, these sea surface anomaly features with what we call the state of the ocean tool. It's our visualization tool. And then we're really going to move on to, I think, why we're here and demonstrate cloud computing with the altimetry and other data and do this scientific analysis and investigation. And that part is going to be led by Jinbo. So a little overview of Podac. We are the NASA Oceanographic Data Creation Center, managing data, oceanographic data from a number of satellite sensors you see on the list here. Primarily today, we're going to be talking about those measurements that are derived from the family of satellite altimeters, beginning with Topix Poseidon in 1992, and then moving on to sensors such as JASON and JASON2 and JASON3 and the recent Sentinel-6A. So these are all missions that NASA either manages or co-manages with partners such as Kinéis and NOAA. On the right-hand side, we see a little graphic of really the entire suite of Earth orbiting satellites and assets that NASA, has built or co-manages or directly manages. Of course, oceanographic measurements are only part of those, but you can see various sensors such as MODIS and Aqua, things like the altimeter family that I mentioned, as well as salinity measurements such as in the past history there was Aquarius and now SMAP. Podac is also involved in situ campaigns and airborne campaigns. So there's been recent sail drone, which are autonomous in situ profile instruments, sailing instruments that have a variety of sensors on them. Airborne campaigns, there's various airborne campaigns that are being planned now for the S-mode mission and preparation of the SWAT, which is the next big decadal altimetric mission that's going to be launched later this year. So we're really talking about what we can observe from altimeters in this particular presentation. I wanted to give briefly a quick shout out to a previous webinar that we gave entitled Surfing Ocean Data in the Cloud. That was last year in August of 21. And this really gave the background of what Podac is doing with respect to migrating its data into the AWS, the cloud, and really the kind of family of and then the ecosystem that's being built around these data sets now, both directly accessing data in S3 buckets or accessing with the AW virtual browse and the various families of tools and services that also have been developed in the Podac and the NASA program as a whole. So we have some command line tools that I'll describe a little bit later, such as Podac Data Downloader that can be used to elegantly download data from the cloud. Of course, there's other familiar services like OpenDAAC in the cloud, and there's also the NASA Harmony services that are homegrown services for things like data discovery, transformation, and subsetting. So have a look at that particular seminar. If some of the details that I'm going to be discussing in this particular seminar are a little bit new to you, we don't really have time to kind of delve into the entire kind of cloud migration that has been occurring for Podac data and NASA data as a whole in this particular seminar. So again, what we're really kind of after is to use some altimetry measurements to look at a global warming signal. And if you want to look at global warming, that's anthropogenic heating that's going in the Earth system, really the oceans is one of the places you really want to look first. And that is because of the various physics of the Earth system. The vast majority of heating that's going in to our climate system is going into the ocean. Of course, the atmospheres and the continents also play a role. They're also heating up. But because of the physics of the ocean and the large heat capacity of water, the vast majority of heating is going into the ocean. So if you want to look for a global warming signal, that's really where you might look first. One of the ways, the proxy measurements for climate signals is to look at sea level rise. So these are measurements directly from the family of altimeters. Radar altimeters that are flying on the instruments, missions such as Topix and the JSON series. So sea level changes due to land ice melt, the thermal ocean expansions, that's the temperature change of the water, and also land runoff in that priority order. I'm going to start a little animation here as I'm talking here on the right-hand side. This is an animation you can find on the internet that was produced recently by us that shows the sea level as measured from the altimeters. There's a time series. So on the right-hand side, you see the measurements that have began in the Topix Poseidon as it goes through time. So these global sea level observations by the NASA CNES altimeters, beginning with topics besides in 1992, really provide the most comprehensive integrated ocean measure of the state of the climate system that compresses both the effects of the ocean, the cryosphere, and the land into the altimeter measurements. There's been about a 20 centimeter total sea level rise since the early 1900s, and in this modern altimeter record, about 10 centimeters since the early 1990s. The other measurements previous to the altimeter we get from high quality tide gauges, and so we can actually extend that sea level rise measurements back to the early 1900s. So about 10 centimeters in the modern altimeter record and 20 centimeters in total. And so you see now the little animation is almost completed, and this is a nice time series stitch between this family of altimeters, starting with Topex, moving on to Jason 1, Jason 2, Jason 3. The Sentinel 6A is not really a part of this particular animation yet, but will be in the future. All right, let me just briefly describe some of the sea level data sets, including what the data sets you just saw in that particular animation. So there's a number of sea level data sets that we distribute from the Podac, and I'm just showing a few of the very popular ones right here. So, the first one is the integrated multi-mission ocean altimeter data for climate research version 4.2, and this is a level 2 data set. That's the data set that actually went in to that particular that's kind of the foundational data set for the number of the other data sets that are followed here, including the next one is the measures gridded sea surface height anomaly version 1812, and this is a level 3 data set. So it has taken that level 2 data set and actually put it on a grid, on a regular grid. There's been some interpolation done to it, so it's a 19 kilometer 5-day product. And then actually we can take all those level 3 measurements or level 2 measurements and compress them into a level 4 data sets. And that's actually what you saw in that little animation there, where we actually average all those measurements kind of on like a 5-day basis, and we globally, and we plot them as a continuous time series that we saw in that particular animation. All right, next I'm just going to show you briefly some visualization of these products, and we're going to actually look at this level 3 measures gridded sea surface height anomaly. So in this case, from the sea surface height measurement, there's been a climatology or a long average removed to it. So it's actually an anomaly measurement, and that's actually really what we want to see. And we're going to use this to resolve the most recent El Nino. And so this is our state of the ocean tool. I'm sure many of you are familiar with it. It's just a visualization tool, kind of a gateway to doing quick and dirty visualization and maybe some cursory investigation. What we're looking at right now is the sea surface height anomalies for a particular day in August 16th, 2016 right here. And the color scale goes from minus 0.3 meters to plus 0.3 meters. So as we see some of these whites here, they're about 0.3, and the blues are minus 0.3. Of course, maybe the best place to depict some of these signals here in the Gulf Stream, where some of the warm and cool core eddies are showing up as both highs and lows in sea surface height right here. What I have loaded up is just an animation, a pre-can animation of the most recent El Nino. I'm just kind of like going to zoom out here so I can see the entire Pacific. We're just going to step through time at a monthly time interval and watch the evolving sea surface height signals. And I'm going to maybe freeze it right there, where we step back into probably about November 15th is the maximum of the particular El Nino feature here. We'll see very high sea surface height data here on the eastern side of the Pacific and very low in the west. We can actually look at some of the data values in this graphic. So if we click right here, we can kind of float over these white values, and they're about 0.3 or greater than 0.3 meters. If we go over here to the low right here, it's around greater than negative 0.3. So kind of the maximum is about a meter from end to end, and that's typically what we see in a very strong El Nino period, that the eastern part of the Pacific Basin is about a meter higher than the western part. So there's also a way from this particular visualization tool to get at the data. There's a little description here, and there are links here to actually get more information from a particular data set that you're viewing, including their data access options. All right, sorry. So I did mention, one of the tools for accessing data that's in the cloud that we've developed is a nice little Python program called the Podac Data Downloader. And this is just an example here of how you implement it or execute it on the command line. It's very quite simple. You just pass it what's known as the short name, and you give like some space-time bounding or some temporal bounding boxes, and you give it a download directory, and then you just execute it. And it, in this case, this particular example I'm showing will download all the particular files that were used in that animation that we saw. So again, refer to the previous webinar, Surfing Ocean Data in the Cloud, really for an overview of the different access and service methodologies for cloud data. But now we're going to move on to, oops, sorry, folks. We're going to move on to the exciting part of this presentation, that really the objective where we wanted to get into a practical example of doing some cloud computing. And this is going to be led by Jinbo Wong. And so here, of course, our objective is to bring the code to the data. So I'm going to pass it over to Jinbo. Jinbo, go ahead and take it away.
Thank you very much, Ed, and thank you very much, Jennifer, for inviting us. I'm Jinbo Wong. I'm the project scientist of Podac. Ed, you quit your screen. Maybe I can take over, Jennifer. Can you pass the presenter mode to me? Okay, great. All right. Are you seeing my screen?
Looks good, Jinbo.
All right. So I'll bring back this slide. The main objective, this is second part of the webinar, is to show you step by step, assuming you have zero knowledge of AWS Cloud, and how you can, from zero to do some calculation in the cloud, taking advantage of the in-cloud access of the AWS S3 data storage and AWS computing resources, so-called bring code to the data or moving code to the data. So this diagram, I want to spend a little bit of time explain what is the benefit of moving code to the cloud. I think most of you already know, but let's just recap what we are doing and what's our target. Can you see my cursor, Ed?
Let's see, move it around a little bit. I do see some, yeah, I do see something.
Yes.
Yes. Is there a way that we can bring it? Okay, here. All right. So here is me preparing this talk and try to analyze some data. All right. So I have two ways of getting to Earthdata Cloud. I can do through internet. The speed usually average 50 megabit per second, and go through Earthdata login and then access Amazon S3. So in this road, as Ed mentioned, we have a fantastic tool called a data subscriber and data downloader. So we can directly download data from Earthdata Cloud hosted in AWS S3 bucket. I can download the data and analyze on my own computer or server. That's the normal way of we doing research. And the second way, which is shown here, is to go through the internet, but without downloading the data. So we have a terminal, local laptop or desktop. We then go through AWS account information, and then access to AWS cloud computing resources, and fire up a computer that is hosted in AWS. So the benefit of that is that computer has a high-speed access to AWS S3 bucket. The speed can up to 100 gigabit per second. That is enough for me to analyze most of the big data hosted in AWS S3. So in this process, also you need Earthdata login, because everything of Earthdata, we need this so-called EDL to access. In addition, there's another layer of AWS credential. So that workflow basically is the same as we normally do. If you are in a large research group, probably you already have a centralized group-owned server, so everybody has an account and you can use password to log in. and then that server has a big computing power attached to a big data storage. So the group share the data, a common data. You can subset and analyze the data there. Now, this cloud-based computing, just imagine that you have AWS as a backup of your research group computing server. So if you have a group of 10, then the server serves 10. Then the AWS cloud is really centralized for the whole community. You can have thousands of working a research group hosted in the AWS cloud, but the workflow is pretty much the same. In addition, is just to add another layer of AWS credential assessment. So in this case, I use 50 megabit per second internet to access to AWS computer. That's a sufficient speed because we are not bringing back the data. We bring back the analysis, the figures, the list of diagnoses, basically a small number of data. And use the AWS computer to directly access S3 bucket and do this data transfer within the AWS facilities, which is really fast. So this is what is the benefit of moving code to the cloud. Now, a year ago, I have nothing in my knowledge base. What is AWS? I don't know what is EC2. Have no concept of what cloud is. In the past year, I have a fantastic team that I learned. So let me remove this annotation. Okay. Now that move to my notebook that I'm going to present to you with all this step-step walkthrough from no AWS account to the end that you run this code, analyze the global mean sea level time series, and hopefully by the end, we will build a website through AWS EC2. Bring your analysis actually broadcast to the web and publish it. As I said, I have zero knowledge of AWS a year ago. I had a fantastic team listed here, and also a team member of the Podac Coding Club has been very fantastic. We meet every week and discuss our struggles and the problems, challenges, and we come up solutions quickly, and that's very good experience. And also a special shout out to OpenScapes. I also learned so much of the cloud related knowledge from by involving OpenScapes. So this is really a group effort. So my talk title is not my talk title, is the talk title is moving code to the data and analyze sea level rise using Earthdata in the cloud. And end of the talk or end of the notebook, we're gonna reproduce this time series purely based on the Podac data in the cloud, which is Earthdata Cloud. Okay, motivation. Again, repeat some of them. You expected that NASA Earthdata will grow to 250 petabyte in 2025. That's really a big data. Excuse me. So cloud computing has a big potential, as we discussed in the diagram. You cannot download 250 petabyte of data for sure. So the path to cloud computing is really unclear for majority of the science application community. We have forerunners, really expert of the cloud computing, but the majority is still in the cloud. Is not very clear where to go, where to start. So we are often perplexed at the start line by new language related to cloud computing, a large amount of different AWS tools and services. If you go to AWS website, you will be overwhelmed by the information, such as CloudFront. What is CloudFront? What is EC2? What is VPC? Right? Bucket, Glacier, Snow Cone, Snowball, Snowmobile, data lakes. Come on, this is, one thing is that AWS definitely like earth science. I think that's a one side. Okay, that's a cheap joke. So now in this talk, we aim to share our experience and pass the experience of passing the start line from 0 and start to run cloud computing. We will do that by demonstrating a use case. So the global mean sea level is an important climate indicator, as Ed alluded to, relatively easy to calculate from Podac data. So that's why we use this as demonstration. So again, this talk is about a technical moving code to cloud. Excuse me. The science behind it is less of a focus, but we're going to just use it as a use case. The objectives specifically just 3. The first one, I will walk you through how to set up a cloud computing environment from scratch. And the second one is run the global mean sea level code in the cloud. The code is in the notebook. You can read it yourself from GitHub. I believe the link is in the chat. And the third one is build a web page server using the same cloud computer and present the graphics that produced by this code. So it's just really to illustrate a potential workflow that if you have application that use Earthdata Cloud, you can use the Amazon computer to do analysis. At the same time, bring the analysis and broadcast it to a web page. So, and you can set up automatic cron job and automatically update the web page. So everything will be automation because of the cloud framework. Again, the target audience is a science application-oriented group who has interest in cloud computing, is familiar with Python, Conda, and Jupyter Notebook, which is the main tool I'm going to use. I know there are a lot of people using other tools, but it's hard to cover everything within this short time. But the audience also will not assumed with a lot of knowledge of NASA Earth data or IT and zero knowledge of AWS cloud. All right, let's get into it. Steps towards running in-cloud analysis. Okay, I assume you have no knowledge of AWS. So first thing you have to do is get an AWS account. This is a very simple step. It has nothing to do with the cloud. It's like apply Amazon account. What you need is your name, email, a phone number, and a credit card. So credit card, we'll get into it because we will have free tier offer from AWS. So you probably will not charge a lot in your credit card. Start an AWS cloud computer. That's the second step. It's like a power on your computer, the same concept. Configure a EC2 with the necessary software. The EC2, by the way, is Elastic Computer Cloud, EC and E and 2 Cs. So configure the EC2 with the necessary software. If you try to relate to your experience, it's like you getting a new computer. You have to install the software in order to process data, to analyze data. The computer come in the box will not likely to have Conda installed, for example. That's something you need to do. This step also is less to do with the cloud, but more to do with the setup the environment for your own calculation. The fourth step is configure a Jupyter Lab on an EC2 and connect to it from browser. This is also related to set up the environment, but a little bit different is that you have to connect somehow to the EC2 remotely in AWS facility to the computing environment. One way you can do is just to basically use the terminal and access it to it. But the Jupyter Lab a project really bring this on a different level. This is a web-based interactive environment for coding. We can get back to that later during this detailed presentation. So the fifth step is demo this code. The code is written and tested inside this notebook. If you yourself pass the 4 steps yourself and download this notebook, you should be able to run this and reproduce the result, no problem. The sixth step is optional. For if we have time, we're going to go to this. Set up a Apache server and create a static HTML web base to show the result. So it's fun there. There are many ways to achieve the end goal, and many alternatives are much smarter than what I'm going to show you here. But my motivation here is to show you move the code to cloud without talking too much about the cloud itself. So because the cloud knowledge base is so vast, we can be easily lost inside. So if I really want to remove all the cloud specific knowledge, but make it relatable to your daily practice. So important terms before we go to understand what does the term mean. The AWS region is basically just the AWS facility. There are many of them, I think 4 in the US. NASA Earthdata are in the US West 2, somewhere in Oregon. I could not find the facility picture on Google. But if you just hear US West 2, it's just referring to a US facility, AWS facility in Oregon is in US West 2. Another is US West 1, I think is Northern California. EC2, as we talked, is Elastic Computer Cloud. Basically, it's just a computer in one of the AWS regions. The computer definition of computer is pretty weak in this case. You need a CPU, you need a memory, you need a disk connected to it. You don't have to use a monitor or display, right? So it's a server. It's just a computer with 3 components in this case. It is a common practice that you should use a EC2 in the region where your data is hosted. So by that, you always start your EC2 from US West 2 region. And the third one is AWS Console. It's a web-based control panel for all AWS tools and services. You will use this a lot if you start to practice AWS Cloud. You can start a EC2 from there, create a storage disk, for example, and much, much more. And a key pair. This is another important term. It's an SSH key generated for accessing a EC2 through SSH, for example. Anyone who has your key can connect to your EC2. So keep it safe, change the mode to readable just to you. But also, on the other hand, it also means that you can share the same EC2 with others, just passing through this key pair file. You can email, you can share. Whoever has this key pair file can access to your EC2. So yeah, by that you can share the same computing environment if you have set it up. All right, so now step 1, get an AWS account. There are 3 options here that we find. Again, if you already have an AWS account, you can skip to step 2 directly. The choices are, first one is the recommended one. Look for institutional support. By now, most of the universities and institutions should have an option of the computer support, not just buy a new computer, but actually provide you cloud credit. So look for that first. That's the easiest and also most official and systematic. You have a proposal, you have a grant, you can actually transfer money to support your computing need. The second one, if you don't have that, you want to get into cloud and get some experience, engage in NASA-funded programs such as OpenScapes. So NASA has these funded programs just to promote the cloud adoption. And most likely, these programs will provide a limited term of a free AWS account for you to practice on. The third option now is our focus today. Assume you have no access to the previous 2. What you can do is really a poor man's solution or rich man's solution. Depends on how you interpret this. It is free for a year, but only offers a small computer The largest computer is 1 CPU, 1 gigabit of memory. It's limited, but it's free. You can actually keep it running for a year without turning it off. It's free. The offer details is 750 hours per month. That's 31 days. And this is called a free tier. By practicing our notebook and testing, we find that this can work for this notebook, but you have to be really careful in the process of installing Conda environment. The 1 gigabit of memory sometimes is not enough. You have a memory error, so you have to really keep an eye on while you install the Conda environment later on. Now the third one is a catch. You need to put a personal information, including credit card. But the is pretty transparent how the charge, and if you just keep within the free tier, you will probably not charge a lot. But there are some other additional charging. If you move a lot of data back and forth, you will get charged. So be careful on that. And so this web page explains the 5 steps to create an AWS account, which is straightforward. I will take some time, so I will not go through this live, but it's pretty straightforward. If you are reading this notebook, you can click this link and try to understand the specific steps. Now, assume you already have AWS account now after step 1. Step 2 is start a EC2. Basically, start a computer. The computer lives in AWS facility, not in your office. So the first thing you do is go through AWS Console. Let's go there. This one, I already have one running, but I can log out and log in again. So log back in. So this is the login page. If I just make it larger, I can do this root user. I saved my account information. There is my personal account. Also, I saved my password through Firefox. So I just click, and then I sign back in. The first thing you will check is the region. This is US West 2. You can see that US West 2 is in Oregon. So I make sure I'm checking the right region. And this is the window that to list the services I recently visited. But if you are logging first time, maybe you don't have this, you can just click the services or search EC2. And then the first one, you can click on the EC2. This will be the EC2 dashboard you will use quite a lot. The first thing you see, this is a list of information. I already have instant running. That's 1. I have 2 key pairs. If you remember, key pairs is just SSH key, and you can ignore others for this talk. So now you want to launch instance. So this is the launch an instant web interface. If we go back to my notebook for the presentation, I listed each step you need to take and each options you need to choose in order to launch this EC2. So I'm gonna just launch real time while I'm presenting this. This is, let me see, this is the name tag. I'll use Earthdata Live. And this one, I choose Red Hat. Nothing special because this is how I built my notebook. You can choose others, but if you choose other platforms or operation systems, my notebook steps might not work exactly. So if you want to walk through the notebook, just choose Red Hat and the free tier eligible for Red Hat Enterprise Linux 8. And the next one is the choice of instance type. You remember EC2 is Elastic Cloud Computer Cloud. Elastic means you can scale up or scale down if you do this drop-out button. There are hundreds of choices you can just browse through, from small to large. So the first option is free tier, 1 CPU, 0.6 gigabit memory. It will not do much, but it will charge you free. But if you beyond 1 and 12 months, you get 2 cents per hour. I'm going to choose not free for this. I will choose this one. It will be 10 cents per hour. And then you can create a new pair by clicking this and enter a new pair, Earthdata, new pair name. And then after you click create new pair, you're going to download this new pair and into your download folder. And then you just click these 2 boxes to allow HTTP traffic, and then that's it. Oops, where did it go? I think somehow it went back. This one, during the dry run, we find this live demonstration kind of start from the beginning and really take time. I already have one started in the background, but I will start this new one. While it's running, I will talk about the rest of the notebook. So okay, so let's just this one now is pending. Let it run, spin up. Let me get back to it. So in this step 2, we have this key pair downloaded, and you can move to a secure place and change the reading mode to 400, and then launch instance. Then by the end of the step 2, you will have EC2 launched. And the step 3 is log in and install necessary software, prepare Earthdata login. So you can go this step by step. This is SSH syntax. You can use this -i, and this is the key pair name. EC2 user is always the same username for the EC2 instance. And this is SSH tunneling to redirect the GUI traffic back to your browser. So you can use your browser to access EC2. And the rest is install the software, the system update, and this block will install the mini conda, and this block will install all the software that you need to run this notebook. One important step is to create a .netrc file. This will save your Earthdata login information. Just to show you quickly the syntax of the Earthdata login. So this is the .netrc file. You have 3 lines, and what you need to change is the username and the password. And save this .netrc in your home folder within the EC2 and change the read permission to 400. Then you're ready to go to access Earthdata in the cloud. Okay, I'm gonna go quickly now because we're kind of running out of time. Step 4 is set up a Jupyter Lab. So after finishing step 3, you already have EC2. You installed all these necessary software from Miniconda and also Jupyter and SciPy and others listed here. You can come back to this and follow exact step 2 into your practice. This is just a 2-line to set up a Jupyter Lab. This setup hashed password, so you can pass it to Jupyter Lab, and this line will get you start a new Jupyter Lab, so you can connect it to it through the web browser. You can see from my HTTP address is really tiny here. So right now I'm showing you my notebook from my EC2 instance already preset before the meeting. Okay, so by the time I already get into this step, the step I'm showing you that use my EC2 to show you the notebook. This notebook is in the Amazon EC2. So the data products we're going to use is the measures SSH version 18.12. There is a new version is available, but this version is in the cloud. We're going to use this one. And also the global mean sea level products produced by Thomas et al. The short name. This is another thing for Earthdata Cloud or Earthdata. One important parameter is the short name. That's the identifier of particular data product. Let's take a look of this global mean sea level product. This is the landing page on Podac website of the information. You can find all the information here and documentation and how to cite here. If you use this data, cite this way. Okay, now let's get to the fun part. And this is the code block. I'm gonna just run. Right now, everything, if I hit the running button, is running in the AWS EC2 because this is just modules, nothing happened. And this, if you read this, this block, read the S3 credentials and pass the credentials and create objects that can read S3 file system. I put some information there. If you're interested in this, you can read the details and what's behind it. That is needed to access Earthdata in the cloud, basically in the S3 bucket. So Podac bucket is called Podac Ops Communities Protected. Everything in here is from Podac. And there's a second level is by short name. So because I already have a short name to the measures SH, I can just press this. It will get all the file according to this pattern. It will take a while. This is the example of the first file name is this. This basically is the S3 file name. If I calculate the number of files is 1,922 files. This block will open this data and show the example of data structure. It's a netcdf. It's in uniform longitude and latitude. This is just one time step. You can see the data variable we are interested in this sea level anomaly in time, longitude, and latitude dimension. Now I'm gonna just do a plot example. This is the first file, and this is sea level anomaly, exactly the data that you saw from the SOTO that Ed presented. Now this block calculates the global mean sea level. We calculate first the area associated with each grade, which is a function of latitude, and calculate the global mean from a particular file in the S3. And also this is the object of the S3 system, and this is the area. The output is a scalar, which is the global mean sea level. Now, if we just demonstrate that, this one, open the first file, and this block will give you the analysis. In the first time step, it is 6 millimeter. Now, this one is going through 26 years with 5 daily SSH field from 1,922 files because it takes time. So I skipped pretty much every year, 72 time step. It will take about 15 to 20 seconds to compute. And in this case, is 18 seconds. The result is saved in result. That's a list. Now here, I just plot it. So here is the global mean sea level over 26 years every year diagnosed. And if we calculate the trend, it's 2.5 millimeter per year. That's a quiz because the global mean sea level from altimetry should be 3.0 millimeter per year. And why did we get 2.5? The hint is aliased because we skipped every year. I'm going to skip the ECCO-based analysis, but just to add the global mean sea level from Frederick Rixey et al. Because it's also in Podac and we can access through OpenDAAC. Also use X-array. This is the data content. we have different variables, or what we're interested in is global average sea level change. And if we plot on top, this is what we get. This is more than 1 century worth of data, and the red is what we analyze based on altimetry. There's another quiz, because if you see this, the trend is different between these two lines. The global sea level trend from tide gauge reconstruction, blue line, is 3.5 millimeter per year. It's steeper than this altimetry-based analysis. Why is that? The answer is altimetry-based analysis does not consider vertical land motion. So you can read Thomas' paper if you are interested in this. Now, this is the last step. I really want to show this. So let's take just 1 minute, finish this. I can start Apache web server through this two line. Okay, now it started. What I need to do is to really copy and paste this to generate an index HTML and put in this HTML server with that Apache's default location. I actually have done it already. So what we need to do is just access it through this IP address. So this is the web page that we just created. So I'm gonna put in the chat, I guess. Where should I put in the chat? So you can take a look at this yourself. This is the IP address. Just copy and paste into your web browser. You will see this web page. This web page is hosted on my personal AWS EC2 that I showed you. It shows the analysis we just did, and that's it. So just quickly, just summarize online materials for using AWS Cloud and Earthdata are abundant, but often organized by topics. So here we focus on building a simple workflow from scratch and show how to do the in-cloud analysis. And it can be achieved with minimal knowledge of AWS Cloud. So we should not be intimidated by so many different terminologies. By repeating these steps, I hope later on you can repeat these steps by yourself. One is anticipated to learn the basic concepts of AWS and in-cloud analysis, as well as Podac and Earthdata Cloud. So apply cloud computing is not difficult, but finding the right path is. Rely on free AWS account linked to personal finance is not sustainable. The community needs a clear official instruction on the channels of getting supported. Support for small size proposals, for example, are needed to advance cloud computing from early adopters to mainstream. So this is a lesson learned from our Podac coding club. A small size coding club with scientists and engineers is very helpful to solve problems faster. Start from basics, that's always helpful, and learn by solving a practical problem like this one. The last one is a restricted cyber environment and needs more attention to virtual private cloud configuration. We actually waste a lot of times to work with GPL and cyber environment. So the future development, we will test the scale up analysis in the cloud. Hopefully next webinar, we can present to you some of our experience with AWS, Lambda, Batch, and HPC. This is actual materials. If you are expert on the DAAC, you can take a look, but I'm gonna stop here, and I will pass this back to you, Jennifer. Sorry for running over time.
Okay, great. Thank you so much, Jinbo. So I think in the spirit of time, since we did run a little bit over, I have opened the optional final polls, but why don't we go ahead and jump right into the questions that have been asked so far. And I really appreciate Catalina and Ed answering some of the questions as we've been going along. So very early on, we had a question. So I want to cover that first. And the question is, can ocean thermal expansion be characterized by sea surface temperature? I think that might have been our very first question, pretty close to the start time.
Yeah, I'll take a crack at that, Jennifer. This is Ed. So the SST is actually just the temperature right at the surface. If you want to measure thermal expansion, you really want to get the integrated temperature signal through depth, really from like a profile measurement. But the nice thing about the altimeters, they're really kind of a proxy measurements of the heat content in the upper ocean. Because as the water expands, it gets higher, it sits higher, and that's what the satellite measures. So I guess my answer is a little bit nebulous. I mean, SST can also be used as a proxy for thermal expansion, but it's really the SST is just measuring the temperature right at the surface, and you're not really getting the deeper thermal signature. So it's perhaps not as accurate for these steric changes as an altimeter measurement is. I hope that answers your question.
Thank you, Ed. And I just wanted to remind our panelists, one way we can avoid any kind of feedback, we'll just each of us unmute when we're ready to speak. I think that'll be helpful. I did hear a little bit for a moment. Okay, so let's move on to our next question. If you could just bear with me for a moment. The next question is a little bit on the technical side. Sorry for being a bit technical. Could we utilize the cloud processing to play around with a long track data level 2 instead of gridded data level 3, and theoretically compare between several correction models, SSB / Lano, / trope / tides, etc.?
Jinbo, did you want to maybe take that question?
Yeah, Ed, I can take that question. Yes, this demonstration is really to start from very, very simple, very basic, very organized data. But the cloud potential is really in the question you posted. Really work on with the level 2 data, which is big, and we don't have to download and analyze in the cloud is really benefiting in that direction.
Okay, thank you so much. The next question was answered, but I do think it would be useful to address this within the webinar. So the question has to do with whether or not will Podac no longer offer data freely? How do I ensure I am not charged in creating an account with AWS?
That's a two separate question. Podac data belongs to Earthdata Cloud. It will always be free for downloading, but creating an AWS account is on a personal side, has nothing to do with Podac. And also, as far as I understand, Podac and Earthdata does not offer cloud account. So this is two separate line of question. Does that answer?
Right.
Yeah.
Thank you. And Ed, you had provided some feedback as well. The next question is, let's see here. And you've kind of addressed this, but I do think it would be valuable to repeat. Is AWS free for this usage?
Yes, for this particular one, we have the free tier from AWS. The usage it has two elements. One is downloading, always free, downloading from Earthdata Cloud. But use AWS computing, that will either charge to your own finance or your own grant.
Okay, thank you very much, Jinbo. The next question is also, if we use AWS, how secure is the data? Does Amazon have rights to any of the data or the findings?
Yeah, let me try to take a crack at that, Jennifer. This is Ed here again. We probably need a lawyer to answer that question, but the security of the data in Amazon is very high. There's a lot of redundancy that Amazon has built into their system, so the data is safe. They don't necessarily, from my understanding, have rights to the data, and they don't have any rights to the results. But for a definitive answer, I think probably we need some legal experts to perhaps answer your question. But I don't think don't have your concern be overblown. There's a lot of science that's already people are doing in the cloud, and I don't think they're really too worried about the Amazon capturing their results or taking ownership of their results. So I hope that addresses a little bit of your concerns, and we'll try to find a better answer for you. Thank you.
Okay, thank you so much, Ed. And we are entering the extended Q&A period at this time. Although some of these questions, again, were answered within the Q&A, I think it's good for us to, some of the participants might have missed this. So the next question is, let's see, will this support remote access like slicing the data we use to do with thread servers and OpenDAAP without going to AWS?
Yeah, I think I tried to answer that question. I'm not sure if I quite understood it, but of course, a lot of the subsetting and discovery functionality you can do in threads and OpenDAAP, you can emulate and even improve upon by running like native Python notebooks, such as Jinbo demonstrated in the cloud. Of course, when you're in the cloud, NASA does have, for example, OpenDAAP in the cloud. So there is an OpenDAAP server that's exposing all this cloud data endpoints in the OpenDAAP service. So that is functionally available. And we're also working towards having threads in the cloud as well. We're not quite there yet. But I think the point is that many of these services that are familiar to you, like OpenDAAP and Threads, once you're in the cloud and doing cloud computing, you'll be able to access and make the same kind of functional calls that you did from your local computing system and have kind of the same expected responses. So I hope that answers your question.
Well, thank you so much, Ed. And just a quick point for everybody. We will provide the Q&A log to our speakers, and so certainly they can follow up with you offline if you have any additional questions and have that conversation. So the next question is really the users were wanting for you to post a link to Thomas's paper on vertical land motion and sea level rise into the chat. And I may have missed that if you already did that, but I do not think I have that link handy.
Jennifer, the link also included in the notebook.
Okay, great. Okay, great. And I've included the link to the notebook a few times, but let me do that again right now so that you can actually reference it. Let me do that really quickly. Thank you for that reminder. That's great. All right. Put the Jupyter Notebook link in again, and let's move on to the next question. And I don't, one of the questions was, and perhaps you addressed this, I'm not sure, but so the question was, this is all running on how many gigabytes of memory? If you could confirm that, Jinbo, I think that would be useful. Ed did provide some input, but I think it would be good to gain a confirmation there.
Yeah.
Some questions about the technical specification of the instance you were working with, Jinbo. If you could clarify that.
Yeah, let me explain. Before the meeting in the test run, I used the free tier, 1 CPU, 1 gigabit. There are hiccups in the installation because the memory error. But in order to run this notebook, after I pass out this error, carefully install the software, this notebook can be run into within 1 CPU and 1 gigabit of computer. I saw that's one particular question from Sanjeev, that how can that be possible to analyze the global data set with 1 gigabit of memory. And if you go back to the notebook, actually I loop through every calculation per file. So each time we calculate it, we are not loading everything. We load just one file, calculate one number. Now, if we have a bigger computer, definitely we can use X-ray MF dataset, for example, to load through everything and use DAAC to do that. But in this demonstration, I want to really focus on the smallest available to us, and we can still achieve this goal. That's built in this analysis flow. For this particular demonstration, I don't want any hiccup, so I start with a large incidence with 4 CPUs and 8 gig memory. But I tested a couple of times, 1 gigabit and 1 CPU works for this notebook.
Okay, well, thank you very much for that clarification. Our next question here is, so let's pretend I do what Jinbo did and compute a SSH average time series. Great, but in reality, I'm not going to want to just have the image, but to have and save the actual time series itself. How does one download the actual results? SCP or something?
Let me share my screen quickly. You can just download from the distributed hub environment. You see, I have GMSL, this picture saved. I can just right click and download. Then it's on my computer. If I have a text file or saved netcdf file, just right click and download. Then that's the easy way to transfer, because you already established the SSH tunneling. All this traffic is encrypted and redirected. You don't have to use SCP. This is already SSH. Hope that answers the question.
Okay, thank you very much. The next question is, our institute has a private cloud account. Is there any way to access NASA data through that?
Yes, NASA data is free, but you do need an Earthdata login account, which is also free. It's just a bookkeeping method for NASA data. So yes, it's free to access, but you do need an Earthdata login.
And I will place the link for setting up a new Earthdata login in the chat in just a few minutes here. All right, so the next question is, how can the demonstrated work be leveraged or integrated with the Harmony system?
Well, maybe I'll try to answer that question. We actually didn't use this particular notebook. We didn't use any Harmony service calls because we just worked with the data as is, and we knew exactly where to go and what part of the time series we wanted to work with. But for example, if you had were looking for a certain, wanted to work with a certain geophysical signal, or you had some idea of the data sets you wanted to use, you would use Harmony services to actually discover the granular endpoints and return those into like a Python dictionary or something like that, and you then use that to make other operations or even other Harmony operations that could do things like spatial and temporal subsetting or some reprojection and things of that nature. So again, yeah, we didn't use any Harmony services in this particular notebook, but in practice, working with kind of NASA big cloud data, you would be probably leveraging pretty heavily on Harmony to do things like granular discovery and maybe even some kind of fundamental data transformation to do it, to get it kind of like to cookie cut it into the region and the time period that you wanted. So that's how you would be using Harmony. And Harmony was described a little bit more in detail in the previous webinar that I referred to you in my part of the presentation. So if you want to learn a little bit more about that, go back and look at that particular webinar. Or there's also the cloud resources. There's a link posted here about the cloud resources that on our Podac homepage. That's also an excellent place to start learning about the Harmony services.
Yeah, just add a little bit quickly. Harmony does have a Python API you can directly import and use in any notebook to access this functionality.
Yeah, thanks for that, Jinbo. I forgot to mention that, but yeah, there is Harmony Pi, right? And you call it directly from your Python notebook as a module and start working with it and executing it, and it's really quite elegant. Thanks.
Okay, the next question is a science question. If you could briefly describe the difference between level 2 and level 3 products, and the further clarification was, is it different for sea level rise only?
Ed, you are
Well,
the expert.
yeah, well, there's it's not different it's not just germane to sea level rise. It's really describing the processing level for the particular data set. So level 2 is typically ungridded data. It's in the native satellite coordinates. It's not on a regular grid. It's not, being level 2 is closer to the native observation, and a lot of scientists prefer that. but some scientists do prefer to work with level 3 data that has taken the level 2 observations and put them on a regular grid. And being on a regular grid just makes them easy, to load into a matrix and to overlay. And it's just an easier way to work with the data. They're in a well-defined coordinate system and a well-defined projection usually. And so at level 3, and then level 4 is generally a merged product or a fused product that takes a number of level 2s and blends them into a level 4. Those are, in many cases, the non-experts or non-domain experts typically like to use those level 3, level 4 products because they're just simpler to use, faster to use, generally smaller in size. But generally every family of measurements, ocean temperature, sea level, ocean salinity, all have data sets at the level 2, level 3, level 4 processing level. Hope that answers your question, and thanks for it.
Thanks very much, Ed. Let's move on to our next question here. We've got about 5 minutes left in the extended Q&A. The next question is, our grad student just asked a good question. If you do some work on an EC2 computer and then log off, where does the data go? Does it remain accessible the next time you log in, or is it gone as when using a supercomputer's memory?
Excellent question. Let me take this by showing my EC2 dashboard. This is my EC2, and you can see this is public IP address is running, and there is a storage here. It's the same thing as your own computer. Once you stop it, you will stop paying for it, but you still keep everything there. It's attached to storage. But there are options that you can also terminate instance. By terminate, you give up these resources, you will lose everything. So usually I just stop the instance if I don't use it, and then reboot it or restart the instance when I want to reuse it. And then by doing stop and start, you keep everything there. But be mindful that for the storage, right now you have 30 gigabit of a free tier storage. If you go beyond that, even you stop the instance, you still pay for the storage. So that's something to keep in mind. But yeah, there's an option. You can keep everything or your work there. And you can actually set up a backup mechanism by attaching additional disk space. This really goes back to the term elastic. You can have scale up options with dramatic with a lot of options there. You can use different computers power. You can use different storage size.
Okay, thank you so much. And as a follow-up, are you paying for a computer or for an instance on the computer?
This is very complicated question. You pay for computer, you pay for storage, you pay for data movement, and you also sometimes you pay for the virtual private cloud services. And also, if you want to fix the IP address, you have to pay for IP address. I think, Jennifer, maybe there's a candidate of another webinar just from the headquarters or AWS to explain us how the budget look like, or how the costs look like. But there are a lot of subtle costs in it. So not only for computing, but storage and data transfer.
Okay, thank you, Jinbo. Let's take this one final question. This might be off topic, but how is Harmony different than CMR?
Yeah, I'll take that. And the CMR is a common metadata repository, so it's the NASA metadata central repository that houses all the collection level and granular level metadata. So Harmony does query the CMR, for instance, when it's doing like granular endpoint discovery, but really Harmony is separate from the CMR in that it is essentially the power of the Harmony is to be able to do not just the the data discovery and the granular discovery, but actually to do like things like subsetting and transformation and reprojection on select data sets. So there is a difference between Harmony and CMR, although Harmony does use the CMR. Thank you.
Okay, thank you, Ed. I think at this point we will wrap up the Q&A. I'd like to thank everybody for your participation this afternoon. And I'm seeing a comment here. I'm not sure why one of the users was indicating he or she is not able to see the questions in the Q&A panel. So I'm not really sure why that is, but I do know that with the NASA WebEx instance, if you asked a question within the chat, that actually goes to, for a participant viewpoint, that actually just goes to the host and to the panelists. But all participants should be able to see the Q&A. So I'll have to look into that a little bit. Okay, so with that, I'd like to thank all of you for your participation. And if there are any final remarks from either Ed or Jinbo, we could do that now. And if not, what we'll do is we'll leave the virtual meeting space open an additional 10 minutes. That gives you a little bit of time to address the optional polling questions if you would like to. We very much appreciate that feedback. And if you think of something else, please feel free to jot it into the chat or the Q&A. Again, I will forward this content to our speakers so they can certainly follow up with you offline if necessary.
Jennifer, this is Jinbo. I want to quickly thank you very much for this opportunity to bring us to talk about Podac. And I also want to say that Podac will continue to help the community to move the workflow into the cloud, also continue to serve high quality Earth data, ocean hydrology, gravity. So take a look at the Podac website, and if you have questions, we are always happy to hear your feedback.
Yeah, thanks, Jinbo. Well said. And, thanks to all the participants as well. I'm glad that we had a nice set of people show up with a lot of interesting questions and user engagements. And I hope you guys can use this presentation as a springboard to really kind of start diving into the cloud computing. And of course, as Jinbo said, the Podac, we're here to help you, to assist you to answer any questions down the road. So thanks all for your participation.
Okay, well, thank you so much, Ed, and thank you, Jinbo, for your final remarks. At this point, we'll log off from the audio component, and I will leave the virtual meeting space open an additional 10 minutes. All right, so thanks so much, everybody. We will hopefully see you at an upcoming webinar. Take care, everybody. Goodbye now.
Bye-bye. Bye.